Hello students, welcome to the EPG Pathshala. I am Ashok Goel from the Department of Physics and Astrophysics, University of Delhi. Today we are going to discuss Hamilton's formalism from the paper Classical Mechanics. So students, let us see what we are going to learn in this module. In this module, you will learn the technique of Legendre transformation to generate a new pair of independent variables from the original pair. What we mean that if you have a pair of variables like in the Lagrangian formalism, we have the variables, they generalize coordinates and the velocities. Now, if we want to go to another pair of independent variables, which may be say generalized coordinates and say momenta, then there is a technique of doing this, and the technique is a Legendre transformation technique, which generates one independent set of pair from the other. So, you will learn to construct Hamiltonian for some simple dynamical systems and to obtain the Hamilton's equation of motion. So, why are we going to the Hamilton formulation? Now, remember that in the Lagrangian formulation, which we have been discussing so far, we obtained second order differential equations of motion for each degree of freedom, that is for each generalized coordinates. So, depending on the degrees of freedom of our dynamical system, we had as many as the degrees of freedom equations of motion which are of second order. This method is extremely well suited for the study of classical fields. There also exists in the literature an alternate formalism in which we have a set of two first order differential equations for each generalized coordinate, as opposed to the case of a Lagrangian formalism in which we have one differential equation, but that is of second degree. So, in the Hamiltonian formalism, we have two differential equations, each of first degree order. This formalism is known in the literature as a Hamiltonian formalism, and this formalism turns out to be vital to the field of quantum mechanics. So, let us discuss about Legendre transformations and Hamilton's equations. As we have mentioned so many times, in the Lagrangian formalism, the Lagrangian is a function of generalized coordinates, say q1, q2, qn, etc., and generalized velocities q1 dot, q2 dot, and it can also be a function of time. So, the Lagrangian is a function of a set of generalized coordinates and the set of generalized velocities and of time if it explicitly depends on time. So, we have defined and now we have defined in the Lagrangian formalism a conjugate momenta. So, corresponding to every generalized coordinate qj, we have defined a conjugate momenta pj as the partial derivative of L with respect to the generalized velocity corresponding to the generalized coordinate q. That is the conjugate momenta to the generalized coordinate q is defined as pj equal to the partial derivative of L with respect to the generalized velocity qj dot. We have seen that generalized momenta in general need not have the dimension of linear momentum, because if you have, for example, the generalized coordinates to be angle, then the generalized momenta would not, L has the dimension of energy. So, generalized momenta, conjugate momenta would in that case would not have the dimension of linear momentum. So, it could have either the units of linear momentum or angular momentum or any other physical quantity depending upon our choice of the generalized coordinate. We saw that in a situation when the Lagrangian does not depend on a particular coordinate q of r, then the partial derivative of L with respect to QR is equal to 0 because L doesn't depend on QR explicitly. But dl by dqr is the momentum conjugate to the coordinate QR, which means that the partial derivative of this PR is the time derivative of PR is 0, that the momentum conjugate to a cyclic coordinate is a constant of motion. So this is an important thing to remember, that if the Lagrangian does not contain a particular coordinate, then the momentum conjugate to that coordinate, which is called a cyclic coordinate, is a constant of motion. In the Hamiltonian formalism, we choose the generalized coordinates represented by the set of quantities qk and the corresponding conjugate momenta designated as a set of pk's. And instead of the generalized coordinates and generalized velocity, we have now generalized coordinates and conjugate momenta as our variables. The problem is to generate a function which is a function h of this new set of generalized variables q and p starting from the Lagrangian, which is a function of q and q dot, that is generalized coordinates and generalized velocity. So we have in this, we have dropped the curly brackets for simplicity. Now this transformation form a set of coordinates, independent set of coordinates q and q dot to the another independent set of coordinates q and pq is achieved by the technique of Legendre transformation. So Legendre transformation in fact is a general technique for generating a pair xg of independent variables from the original pair xy. So if you have a pair xy of two independent variables and you want to generate another pair which is independent, say x and z, then this is the technique. This is the transformation which you use, Legendre transformation. Consider a function of two variables, a function x and y, and define an independent variable z, like the conjugate momenta p instead of q dot. Then and construct a function g of the two variables now of z and y from the function of x and y, where this function z is defined as the partial derivative of f with respect to x. For example, if f is the Lagrangian and x is the generalized coordinates, then this z is the corresponding conjugate momenta. The function g of two variables z and y is now defined as the function g of z and y is equal to z times x minus the function f of x and y. Taking the differential of this function g, we have dg is equal to x dz plus z dx minus df by dx dx minus df by dy dy. That is, f is a function of two variables and the first expression here has two variables z and x. So the differential of this new function g is obtained by using the chain rule, as therefore dg is equal to x dz plus z dx minus z dx, because df by dx is defined as z minus df by dy into dy. That is, dy is equal to x dz minus df by dy into dy. Now, since g is assumed to be a function of only z and y, therefore the differential of g is dg by dy into dy. So from these two expressions, we immediately obtain that the partial derivative of the function g with respect to the variable z is equal to x, and the partial derivative of the function g with respect to the variable y is equal to minus time the partial derivative of the function f with respect to y. So these are the necessary relations required to get the function g, which is a function of variables z and y, so from the function of x and y. So given a function of x and y, we obtain a new function which is a function of z and y. These are the necessary conditions for that, where this new variable z is defined as the partial derivative of f with respect to x. We can thus define a function h of variables pi, qi, and time t. See, the Lagrangian is a function of the generalized coordinate q and the generalized velocities q dots and the time t. We want to construct a function which is a function of the generalized coordinate and the conjugate momenta p. So, which is a function of p and q, the generalized coordinates and the corresponding conjugate momenta, is defined as this function h of q, p, and t as sigma pi qi dot minus the function which is the Lagrangian in this case, the Lagrangian, which is a function of the generalized coordinates and the velocities and may also depend on time. The function h so defined is known as the Hamiltonian of the system. Its total differential is given by dh. Now differential of this function h is a function of q, p, and t. Therefore, now see, we have written q, p, and t where for brevity, because q now stands for all the generalized coordinates q1, q2, qn, if they are n generalized coordinates, and p stands for all the conjugate momenta p1, p2, p3, pn. So therefore, the total differential of this function h, dh, by the chain rule is given by dh by dq, a partial derivative of h with respect to the generalized coordinate into the differential of the coordinate, that sigma over I partial derivative of h with respect to qi into dqi plus dh of dpi into dpi plus the partial derivative of h with respect to time into dt. Now the total differential of the right hand side is sigma pi into dqi dot plus qi dot into dpi minus dl by dqi minus the partial derivative of L with respect to qi dot minus dl by dt. Where L is a function of the coordinates and generalized coordinates and generalized velocity and the time t. But we have the partial derivative of L with respect to qi is equal to ddt of dl by dqi dot, which is the equation of motion. And dl by dqi dot is defined as pi, so it is the total derivative of pi with respect to time, which is pi dot, and therefore dl by dqi dot is equal to pi dot. Using these, in the expression for the total differential of dh can now be written as dh is equal to sigma over I qi dot into dpi minus sigma over I of pi dot into dqi minus dl by dt into dt. Now comparing these two equations, we immediately get that the partial derivative of h with respect to the ith generalized momenta, that is dh by dpi, is equal to qi dot. That is the partial derivative of the Hamiltonian with respect to the ith conjugate momenta is equal to the time derivative of the ith generalized coordinate, and the partial derivative of h with respect to the ith generalized coordinates is equal to minus times the time derivative of the ith conjugate momenta, and the partial derivative of h with respect to time is equal to minus the partial derivative of L with respect to time. And this holds for all generalized coordinates. So we get a set of 2n first order differential equation of motion. Because dH by dPi is equal to Qi dot is a set of n partial differential equations, first order. dH by dQi is equal to minus Pi dot is another set of n first order partial differential equations. So these equations are known as Hamilton's equations or the canonical equations, and the advantage or the difference of these equations of motion as compared to the Lagrangian equation of motion is that these equations are of first order differential equations, whereas the Lagrangian equations are second order differential equation. But the price we have to pay to go from a second order differential equation to a first order differential equation for equation of motion is to double the number of equations of motion. So this set of equations is known as the Hamilton's equations or the canonical equations of motion. How the Hamiltonian is related to the conservation laws. We know that in Cartesian coordinates, the kinetic energy of a system is given by T is equal to half sum over I mi into Vi square. A particle of mass mi has a velocity Vi, its kinetic energy is half mi Vi square. If the system consists of n particles, then total kinetic energy in Cartesian coordinates is simply given by half mi Vi square, and Vi square can be written as, that is Ri dot square, where Ri dot is dRi by dt, which is the velocity. One thing one must keep in mind here, that when we talk of the time derivative, the dot represents the time derivative and is not a partial derivative, it is a full derivative. The Cartesian coordinates can be expressed in terms of generalized coordinates, q1, q2, qn, etc. That is, the Cartesian coordinates Ri are functions of the generalized coordinates q's, where I runs from 1 to n, the number of particles. The velocity Ri dot can be expressed as Ri dot is equal to dRi by d, the partial derivative of the velocity of the ith particle with respect to the jth generalized coordinate multiplied by qj dot. See, it's easy to see because Ri is a function of the generalized coordinates and time t. Therefore, its total derivative with respect to time can be obtained by the usual chain rule, and Ri dot can be written as dRi, that is partial derivative of Ri with respect to qj multiplied by qj dot plus partial derivative of Ri with respect to t, sum over all j's. And therefore, the kinetic energy in terms of generalized coordinates and the Cartesian coordinates, which are expressed in terms of generalized coordinates themselves, can be written as T is equal to half mi sigma over j dRi, partial derivative of Ri with respect to qj into qj dot plus partial derivative of Ri with respect to t and square of the whole thing. Now, this kinetic energy term, when it is expanded, when the square is expanded, has three terms. The three terms, one term is constant. It doesn't depend on generalized coordinates. The other term is quadratic in the generalized velocities. And the third term is linear in the generalized velocity. So the kinetic energy term T in terms of generalized velocities can be written as a term A, which is a constant term, does not depend on the generalized velocity, plus sigma over j aj qj dot plus a term which is quadratic plus sigma over jk ajk qj dotted with qk dot, where these quantities like a sub j and a sub jk are functions of only the Cartesian coordinates Ri. And in fact, it's easy to see that a is nothing but half mi into dRi by dt whole square. Sum over all i's mi times the partial derivative of ith coordinate with respect to t multiplied by the partial derivative ith Cartesian coordinate with respect to the jth generalized coordinates, and ajk is equal to half sum over I mi dri by dqj into dri by dqk. Now, if the constraints are holonomic and silurinomous, the transformation equations do not contain the time explicitly, and in that case, the partial derivative of the coordinate Ri with respect to t is 0. Therefore, the kinetic energy term does not have a constant term or a linear term. So, for the holonomic constraints, and which are also silurinomous, that is, the system is conservative and doesn't depend on time explicitly, the kinetic energy term then reduces to a purely quadratic expression in generalized velocities. Hence, in this case, the kinetic energy can be written as a homogeneous quadratic function of generalized velocities. That is, the kinetic energy T can be written as a sum over J and a sum over K, that is a double sum over J and K, of some quantity ajk, which is the coefficient of the product of the generalized velocity qj dot into qk dot. And this is a very important result, and in most of the system we will be interested in all the holonomic, and most cases we don't have explicitly time dependence. In that situation, the kinetic energy is simply a quadratic function of generalized velocities. And in fact, as you know, that kinetic energy in fact is a quadratic function of the velocity for Cartesian coordinates anyway. And therefore, the partial derivative, partial derivatives satisfy that sum over I of the partial derivative of the kinetic energy with respect to the ith generalized velocity multiplied by the qi dot is equal to 2 times the kinetic energy. Now, if the constraints are holonomic and silurinomous, the transformation equations do not contain the time explicitly, and in that case, the partial derivative of the coordinate Ri with respect to t is 0. Therefore, the kinetic energy term does not have a constant term or a linear term. So, for the holonomic constraints, and which are also silurinomous, that is, the system is conservative and doesn't depend on time explicitly, the kinetic energy term then reduces to a purely quadratic expression in generalized velocities. Hence, in this case, the kinetic energy can be written as a homogeneous quadratic function of generalized velocities. That is, the kinetic energy T can be written as a sum over J and a sum over K, that is a double sum over J and K, of some quantity ajk, which is the coefficient of the product of the generalized velocity qj dot into qk dot. And this is a very important result, and in most of the system we will be interested in all the holonomic, and most cases we don't have explicitly time dependence. In that situation, the kinetic energy is simply a quadratic function of generalized velocities. And in fact, as you know, that kinetic energy in fact is a quadratic function of the velocity for Cartesian coordinates anyway. And therefore, the partial derivatives satisfy that sum over I of the partial derivative of the kinetic energy with respect to the ith generalized velocity multiplied by the qi dot is equal to 2 times the kinetic energy. Now, for conservative systems, the potential energy also does not depend on velocities. Therefore, the partial derivative of u with respect to the generalized velocity dqi dot is equal to 0. Therefore, the momentum conjugate to the generalized velocity qi namely conjugate momenta Pi, which is defined as dl by dqi dot, depends only on the kinetic energy, and Pi is then given by the partial derivative of the kinetic energy is a function only, is quadratic function of generalized velocities, and the potential energy does not depend on the velocities for conservative system. Therefore, the momentum which you conjugate to the generalized velocity is defined as the partial derivative of L with respect to Qi dot becomes equal to the partial derivative of only the kinetic energy term with respect to Qi dot, because U doesn't depend on Qi dot. Then from the definition of the Hamiltonian, which is H is equal to sigma over I Pi Qi dot minus L. So Pi being dt by dqi dot. So substituting that and substituting for L, which is T minus U, the Hamiltonian then is equal to 2 times the kinetic energy minus the Lagrangian, which is T minus U, and therefore the Hamiltonian reduces to T plus U, which is the total energy of the system. So it turns out that though the Hamiltonian, like the Lagrangian, has the dimension of energy, only in special cases does it correspond the total energy of the system. So Hamiltonian H is equal to the total energy of the system only if for the case of holonomic and celulonomous systems which are conservative. Hamiltonian is a function of the generalized coordinates, conjugate momenta, and may also depend explicitly on time. Therefore, the total time derivative of the Hamiltonian is given by the chain rule. So dH by dt is sigma over I partial derivative of H with respect to Qi into Qi dot plus sigma over I partial derivative of H with respect to Pi multiplied by Pi dot plus the partial derivative of H with respect to T. So now using the Hamilton equations, dH by dqi is minus Pi dot and dH by dpi is Qi dot. So the total time derivative of the Hamiltonian can be written as sum over I of minus Pi dot Qi dot minus plus Qi dot Pi dot plus the partial derivative of H with respect to time, which is the same thing as minus the partial derivative of L with respect to time. So using Hamilton's equation, which we are given in equation 711 and 712, we have seen the Hamiltonian is a constant of motion and that it is conserved if it does not depend on time explicitly. With the help of some examples, we will now illustrate how to construct the Hamiltonian. Consider the motion of a particle in a central force field so that its potential energy function U depends only on R, which is x square plus y square plus z square under root. The Lagrangian being the difference of the kinetic energy and the potential energy is then equal to half m x dot square plus y dot square plus z dot square minus u of r. Now, the momentum conjugate to the coordinate x, that is px, is given by the partial derivative of the Lagrangian with respect to the x component of the velocity, x dot. Since u doesn't depend on the velocities, so px is simply equal to mx dot. And likewise, the momentum conjugate to the coordinate y is my dot and pz is equal to mz dot. The Hamiltonian is therefore H is equal to, from the definition of the Hamiltonian, Qi dot Pi minus L. So we have the Hamiltonian H given by x dot Px plus y dot Pi plus z dot Pz minus L, which is equal to 1 by m Px square plus Py square plus Pz square, because x dot is equal to Px by m, y dot is Py by m, and so on, and minus the Lagrangian, which is half m px square plus py square plus pz square plus ur. Therefore, the Hamiltonian becomes simply equal to p square by 2m plus u of r. The Hamiltonian is therefore h is equal to, from the definition of the Hamiltonian, qi dot pi minus l. So we have the Hamiltonian h given by x dot px plus y dot py plus z dot pz minus l, which is equal to 1 by m px square plus py square plus pz square, because x dot is equal to px by m, y dot is py by m, and so on, and minus the Lagrangian, which is half m px square plus py square plus pz square plus ur. Therefore, the Hamiltonian becomes simply equal to p square by 2m plus u of r. Now, Hamiltonian equation of motion are given by dh by dx is equal to px dot. Now, h, if you look at the expression for h, is only the kinetic energy that depends on the coordinates. So, px dot is equal to du by partial derivative of u with respect to x, and x dot, which is defined as a partial derivative of h with respect to px, is equal to px by m. So, we get px equal to mx dot and px dot is equal to mx double dot, and therefore the equation reduces to the usual equations, and really nothing much is gained, because from this, substituting for px dot, which is px dot is equal to mx double dot, so we get mx double dot is equal to du by dx, which is px dot. So, and similarly for y and z components, and which are nothing but the familiar Newton's equations, or we recover the Euler-Lagrangian equations, and in fact nothing seems to have been gained. First term is x dot plus 2 beta x dot is square, because second and third term do not depend on x dot. So its partial derivative of the second and third term with respect to x dot vanishes, and therefore the momentum conjugate to the coordinate x is simply x dot plus 2 beta x dot is square, which is equal to 1 plus 2 beta x into x dot. So now the Hamiltonian h is defined as px dot minus l, so which can be easily seen to be of the form 4 times p divided by 1 plus 2 beta x whole square into beta x plus beta xp divided by 1 plus 2 beta x minus half omega square x square minus alpha x cube. Expressed in this is given in terms of Hamiltonian is expressed in terms of coordinate x and the conjugate momenta p. As yet another example, let's consider the Lagrangian of a particle moving on the surface of a cylinder of radius a in the presence of a force which is equal to minus kr, that a force is proportional to the displacement and restoring in nature. In cylindrical, so the force F is equal to minus kr is expressed in terms of the Cartesian coordinates. Now, since the particle is constrained to move on the surface of a cylinder, it is more convenient to use the cylindrical coordinates r, z and phi. So we write down first the Lagrangian of a particle in terms of cylindrical coordinates. So the kinetic energy expressed in terms of cylindrical coordinates is half m a square phi dot square plus z dot square, because the cylinder has a radius a which is fixed. So it has only, the particle is moving in the surface of the cylinder, so it has only 2 degrees of freedom, which in terms of cylindrical coordinates we express as phi and z. So the kinetic energy of the particle moving the surface of the cylinder is equal to half m a square phi dot square plus z dot square, and the potential energy is half k r square, and in the cylindrical coordinates is half k a square plus z square. Now, in order to construct the Hamiltonian and the Hamiltonian equation of motion, we first obtain the conjugate momenta, that momentum conjugate to our generalized coordinate phi, and the generalized coordinate z, which we have chosen to be the cylindrical coordinates. So the momenta conjugate to the coordinate phi, namely p phi, is equal to partial derivative of L with respect to phi dot, which from the expression above is nothing but ma square phi dot, and the momentum conjugate to the coordinate z is p sub z is equal to dl by t z dot is equal to m times z dot. And now the Hamiltonian is given by pi qi dot minus L. So we have p phi dot plus pz z dot minus L, which then is equal to half p phi square by m a square plus half p phi square by m plus half k a square plus z square. So we have now the Hamiltonian written in terms of the conjugate momenta p phi pz and the generalized coordinates which were taken to be z and phi. And we see that Hamiltonian is independent of phi. The Hamiltonian equation of motion are easy to write down. We have p phi dot is equal to minus the partial derivative of h with respect to phi, and since there is no dependence of the Hamiltonian on phi, p phi dot is equal to 0. That means the momenta conjugate to the coordinate phi is conserved, and pz dot is equal to minus the partial derivative of h with respect to z is minus k times z. Therefore, the equations become phi dot is equal to dh by dp phi is equal to p phi by ma square, and z dot is equal to partial derivative of h with respect to pz is equal to pz by m. So, from the first equation which says p phi dot is equal to 0, so we have p phi dot and p is equal to ma square phi dot is the integral of motion. So first equation gives us an integral of motion where p phi dot is a constant. The other two equations they can be combined to give us z double dot plus k by m times z is equal to 0, which is the equation of a oscillator, and solution is straightforward. As a final example, we'll obtain the Hamiltonian and the equation of a motion of a charged particle in the electromagnetic field. Earlier, we obtained the Lagrangian of a particle in the presence of electromagnetic field, and if you remember, the Lagrangian of a particle in the presence of electromagnetic field was given as L is equal to T minus a quantity which is q phi minus q by c v dot a, where v is the velocity, q is the charge of the particle, phi is the scalar potential, and a is the vector potential. For a particle, in terms of the Cartesian coordinates, the kinetic energy is half mv square. So L is equal to half mv square minus q times phi minus 1 upon c v dot a. Now, in terms of the scalar and vector potential, we know that the electric field E is given by minus gradient of phi minus 1 upon c dA by dt, where c here is the velocity of light, and the magnetic field B is nothing but curl of A. From the Lagrangian, we have the canonical momenta. Pi is partial derivative of L with respect to the ith velocity, that Pi is a dl by dvi. So we have taken the derivative of L with respect to vi. So Pi is equal to mvi plus q by c ai, where I here stands for the component of the. Therefore, the momenta, the canonical momentum P is equal to the momentum mv, the Cartesian momentum, plus q by c into the vector potential. So this is an important result, that in the presence of electromagnetic field, the conjugate or the canonical momentum of a charged particle can be written as a sum of the momentum of the ordinary momentum mv of the particle plus a term which is q by c into the vector potential. The Hamiltonian now, from the definition, can be written as Hamiltonian being pi qi dot minus L sum over all I. So it becomes a scalar product of the canonical momentum P with the velocity V minus L. And for the canonical momentum P, we have the expression P is equal to mv plus q by Ca. So substituting that, we can simplify this expression and we get H is equal to T plus q phi. Now, the kinetic energy T can be expressed in terms of the canonical momenta, and it can be written as T is equal to 1 by 2m P minus q by Ca whole square, where A is the vector potential. Therefore, the Hamiltonian becomes 1 by 2m P minus q by C whole square plus q phi. This is the form of a Hamiltonian of a charged particle which is used in quantum electrodynamics. Having obtained the Hamiltonian, we can now write down the Hamilton's equation of motion, namely r dot, which is equal to the velocity, is given by the partial derivative of h with respect to the momentum p, and which is seen to be 1 by m p minus q by c a. So you can see that in the r dot is simply p by m. In the presence of electromagnetic field, this momentum p is replaced by p minus q by c into the vector potential A. And the other Hamilton equation becomes minus p dot is equal to like dh by dxi. So it's a gradient of h which is equal to q gradient of phi plus 1 by m p minus q by c dot minus q by c v dot a. So we get q gradient of phi minus q by c v into gradient of a, which then becomes equal to p dot is equal to minus q gradient of phi plus q by c gradient of v dot a. So the Hamilton's equations are then r dot is equal to 1 by m p minus q by c into a, and the other equation is p dot is equal to minus q gradient of phi plus q by c gradient of v dot a. So student, let us summarize what we have learned in this module. What we have learned in this module is that Hamiltonian is a function of generalized coordinates and conjugate momenta as opposed to the Lagrangian, which is a function of generalized coordinates and generalized velocities. Number 2, Hamilton's equation of motion is a set of two first-order differential equations for each generalized coordinates. Number 3, for the case of holonomic, time-independent conservative systems, the Hamiltonian turns out to be nothing but the total energy of the system and is a constant of motion.